Assalamu alaikum students. So today our topic is the stream function, and stream function is used to do two things. One is to define our equation for streamlines, as you remember the streamlines, and the other is to represent two velocity vectors, that is the u velocity vectors and v velocity vectors, as a single term, and that term is our psi term, and this psi term is called the stream function. So the stream function does two things. It gives us our equation to our streamlines, and as you remember the streamlines, we defined our streamlines that these are the lines that are tangent to the velocity field. So this is what it does. Initially we are going to write our equation for our streamlines, and then in the second slide we are going to see how does it satisfy that equation, that stream function, how we are using that stream function to gives us our equation of the streamline. And then in this slide what we are going to do, we are going to represent our two velocity vectors in our differential form of continuity equation, that is the u velocity vector and the v velocity vector, as a single term, that is the psi term, and that is our stream function. So first, this is what our definition for the streamline was, and the streamline is a line that is tangent to the velocity field. And to give you a better visualization of that, let's use this diagram, and in this diagram you can see that these lines are tangent to the velocity vector, and here is our velocity field, and this is a line tangent. A streamline is a line that is everywhere tangent to a velocity field, and these are our streamlines. So we already defined that, and if we can use this diagram right here to write an equation of a streamline, so we can use this diagram to write an equation for a streamline, and then in the second slide what we are going to do, we are going to use the stream function to derive that equation. So by using this diagram we can actually write the equation for a streamline, and here you can see the streamline. This black arrow is a streamline, and this blue arrow is the v velocity field, and this v velocity field has two velocity vectors, that is the v velocity vector along the y-axis and the u velocity vector along the x-axis, and this v and u velocity vector are along a certain differential y and x-axis. So using these two triangles and using the tangent theta, we can relate these two triangles by this term right here, that is that dy over dx is equal to v velocity vector over y velocity vector, and this is what the slope of the tangent is. If we take the slope of these two triangles and relate it, so we will get these two terms, that is our dy over dx is equal to v over u, and we can take the slope of these two triangles by taking actually the tangent theta of these two triangles, and the tangent theta of the smaller triangle will come out to be dy over dx, and the tangent theta of the bigger triangle will come out to be v over u. So we are actually comparing these two equations, that is dy over dx is equal to v over u. So this is our equation for the streamlines. So we are going to derive this equation by using the stream function, but first what we are going to do is see that how the stream function helps us to represent two velocity vectors, that is the u velocity vector and v velocity vectors, as a single term, and that single term is called psi, and that psi term is also called our stream function. So to do that, what we are going to do, we are going to take our differential form of continuity equation in two-dimensional flow field. So in two-dimensional flow field, this is how our differential form of continuity equation will look like. We already derived that in the previous lecture, and this differential form of continuity equation is for steady, incompressible, plane two-dimensional flow. So if we are taking these assumptions as if our flow is steady, it is incompressible, and it is in a plane two-dimensional flow, then this is how our differential form of continuity equation will look like. So what the stream function does is it gives us a single term psi to represent these two velocity vectors. That is, we can write this psi in terms of u and v, and we can also write these u and v velocity vectors in terms of psi. So you can see that by representing these two velocity vectors with a single term, we will get one unknown, that will be psi for this single equation. And right now you can see that we have two unknowns, that is the u velocity vectors and the v velocity vectors in this single equation. So by representing these two velocity vectors by a single psi term, we can actually get one unknown and one equation. So let's see how we are going to use this psi term. So to move forward, let's again define that velocity components in a two-dimensional flow field can be expressed in terms of a stream function, and this is how we are going to represent our two velocity vectors. This is our u velocity vector, and that u velocity vector is equal to partial psi over partial y, and this is our v velocity vectors, and our v velocity vector is equal to minus partial psi over partial x. So if these equalities are right, then it must satisfy this continuity equation. So let's put these two values, the u velocity vector and the v velocity vectors value, in the differential form of continuity equation, that is for a steady, incompressible and plane two-dimensional flow. So by putting these values in the differential form of continuity equation, this is what we are going to get. This is the partial y over partial x term right here. This is what that term is, and by putting the u velocity vector as partial psi over partial y right here, you can see now, and this is plus the partial v over partial y term, and here we have put the v velocity vector as minus partial psi over partial x. Now multiplying these two terms, we get partial square psi over partial x partial y, and minus partial square psi divided by partial y over partial x. So you can see that these two terms are equal, and they will cancel out to be 0. So actually these two terms, that is u is equal to partial psi over partial y and v is equal to minus partial psi over partial x, also satisfies our differential form of continuity equation. So we can use right now our stream function to represent these two velocities by this single term psi. And here you can now see, you can also say that this is our differential form of continuity equation. This right here is also our differential form of continuity equation, and here this psi term is actually representing these two velocities. So what we have done, we have taken these two terms out, the u and v velocity vectors, and now we are representing it with a single term psi right here. So now we have one equation and we have one unknown. So this makes our calculations easy, as you already know, because having one equation and one unknown, we can actually have a absolute solution. By having two unknowns, that is in case of u and v velocity vectors, we will have one equation, that is right here. So this is more suitable for us, and this is more easy for us to deal with, because right here we have one unknown and one equation. So this is what the stream function is used, and this is its one advantage, and that advantage is by representing these two velocity vectors, the u and v velocity vectors, as a single term, and that term is our psi term, and that psi term is called our stream function. So this is its first advantage. Its second advantage is it also can be used to derive the equation for our streamline, and that was our equation for our streamline. And now in the second slide, what we are going to do, we are going to use this stream function to derive this equation right here. So now moving on to the next slide. So this was our equation for our streamlines, and now we are going to use our stream function to derive this equation. So what we are going to do, we are going to take 2 points. One is point 1, the other is point 2, and point 1 is, let's say, at xy, and as this point moves from point 1 to point 2, its coordinates change to x plus dx and y plus dy. So let's say we have a function psi at point 1. So how will this psi change when it moves from point 1 to point 2? So let's see that the change in the value of psi as we move from one point xy, that is the xy, to a nearby point, that is x plus dx and y plus dy, is given by relation. So we can actually write a relation from this change as we move from one point to another. We can write the change, a relation for the change in psi. So that change in psi, that is d psi, is equal to partial change in psi along the x into dx plus partial change in psi along y into dy. And we can actually substitute these terms, that is partial psi over partial x by minus v and partial psi over partial y by u. We already wrote these terms, minus v is equal to partial psi over partial x and u is equal to partial psi over partial y in the previous slide. So what we are going to do, we are going to take a line along which this psi is equal to constant. So actually we are going to consider that the stream function is constant along a certain line, is equal to a constant. So by taking the change of a constant, by taking a derivative of a constant, what we get 0. So if we equate this equation is equal to 0, that is minus v dx plus u dy, we can actually rewrite that in terms of our equation, and that equation will come out to be dy or dx is equal to v over y. We can actually write that equation like this. So this is our equation of our streamline. So along a line at which this psi is a constant, we have d psi is equal to 0, so that this equation becomes equal to 0, and we can actually rewrite this equation in terms of our equation for our streamline. So by using stream function, we have actually now a new definition for our streamlines, and a streamline is a line along which this stream function will be equal to a constant. So if we take certain lines and along that lines the stream function is a constant, we can actually plot our streamlines. And by plotting our streamlines, what we actually do, we actually get a better sense of visualization of our flow field. So if we place an obstacle in our flow, we can actually see how that flow will behave when it strikes that obstacles. As you can see in this figure, that how that fluid will behave, and we can only see that by the help of these streamlines. And we can actually plot these streamlines by taking psi is equal to a constant along these streamlines. So by taking this condition and applying it on these lines, we will actually be getting our streamlines, we will be plotting our streamlines, and by plotting our streamlines we will get a better visual representation of our flow. So this is what the stream function, this was our stream function psi, and stream function psi is used for two purposes. One was to represent the two velocity vectors in the two-dimensional differential form of continuity equation, that was the u velocity vector and the v velocity vector, as a single term psi, and the other is to take psi along a certain line constant, and by taking psi along a certain line constant, we are actually defining our streamlines, and by defining our streamlines, we are getting a better visualization of our flow. So this is what the stream function is used, and the stream function is used for these two purposes. So now let's move on to our conservation of momentum, and let's derive an equation for our conservation of our momentum in a differential form. So let's do that. So now let's talk about the conservation of linear momentum, and as you remember, we already derived a term for the conservation of linear momentum for a finite control volume by using the Reynolds transport theorem, and this is the term we derived for a finite control volume. So this was our Reynolds transport theorem in terms of conservation of linear momentum, and that was the summation of forces of the control volume is equal to the partial change with respect to time of momentum inside the control volume plus the momentum exchange across the controlled surfaces. So this equation, as you know, for any equation has two sides, that is the right hand side and the left hand side. If we take the right hand side, this right hand side can be applied for a very small control volume. Means if this is a very small control volume, that is delta V, so this right hand side can also be applied to this small control volume. Means that for an infinitesimal amount of control volume, this right hand side will remain the same, and this right hand side will again contain the term for the partial change in momentum with respect to time inside the control volume. So if this is our small amount of control volume, this will be the change in momentum inside the control volume, and the momentum exchange across the control surfaces means the momentum that is being exchanged when this flow goes in and out of this small control volume. What we will be more concerned in this, as you know, this, as we already defined, will be the same. This right hand side will be the same for a very small control volume. What we will be more concerned about is the forces. That what will be the forces and how will we define these forces when these forces are applied on a single fluid particle. So we will be more concerned about the left hand side of this equation, because we already said that the right hand side equation can be written in the same manner for a small infinitesimal amount of control volume delta V, but we cannot take the same forces and apply them for infinitesimal amount of control volume. When we talk about an infinitesimal amount of control volume, let's say we are talking about a single fluid element right here. So what will these forces be when they are applied on a single fluid particle? That's what we will be more concerned about in this conservation of linear momentum when we write it in a differential form. And we will write our equation of motion, that is F is equal to ma for a single fluid particle, and then we will see what these forces will be when these forces are applied on a single fluid particle. So we will talk about two forces. These are the body forces and the surface forces. So in general, these two forces will be responsible for the change in momentum for a single fluid particle, and we will write this equation of motion F is equal to ma when we take our body forces, and we will similarly use this same F is equal to ma, our equation of motion, when we write an equation and take surface forces as the forces that are being applied on the single fluid particle. So for a body force example, we will take our gravity. Gravity is an example of our body forces, and for surface forces we will take pressure, and due to pressure a certain amount of stresses will generate. So we will talk about the stresses. These stresses will include both our normal stresses, these are our normal stresses, and our shear stresses. So this is what we are going to talk about when we talk about the differential form of conservation of linear momentum. We will take the same right hand side in this equation and apply that for a small infinitesimal control volume. This right hand side will not change for this infinitesimal control volume, but this left hand side will be changed, and we will further classify this left hand side. These are the summation of forces into body forces and surface forces. We will take our body force as our gravity because it acts as a whole on this body, and surface forces that are pressure, and due to pressure the stresses that are being generated because the surface forces generate when the fluid comes in contact with another surface. So this is what we are going to talk about in this conservation of linear momentum section for our differential analysis, and we are going to write our equation of motion F is equal to ma when we take our forces as our body forces, and F is equal to ma when we take our forces as our surface forces, and what will be the stresses that will be generated in that regard. So let's take our left hand side of our equation and write it like this, so that the force that is being applied will result in a change in momentum. So F right here is the resultant force. This is the resultant force acting on a fluid mass, and what will happen? A change in momentum will happen. So if P is the linear momentum defined, P is equal to, that is V dm, that is the change in momentum for a differential amount of mass, and we can also write that equation in this form. So that is delta F is equal to d by dt, that is our material derivative being applied on mv, that is our differential amount of mass having velocity v. So from this equation we can derive our equation of motion for a single fluid particle like this. So this delta F will be equal to delta m dv by dt, and this total change in velocity with respect to time will give us acceleration of our element. So thus this equation will become delta F is equal to delta m and a. So now this is our equation of motion for a single fluid particle, and now we will write this equation of motion when we take our body forces and our surface forces. So this is what we are going to do. We are going to write this equation of motion when we take our body forces and apply them on a single fluid particle, and how will we write this equation of motion when we take the surface forces, and then at the end we will combine these two equations and we will get our single equation of motion for our single fluid element that will contain all the body forces and the surface forces and the resultant change in momentum that occurs due to the application of these two forces. So now let's move on and take our body forces and surface forces and write some equations. Now let's see what the description of our forces will be when we talk about our equation of motion and we take the force, that is F is equal to ma, in terms of our body forces and in terms of our surface forces. So as you can see that both the surface forces and the body forces generally act on a single fluid particle. So if we take a body force, then a body force, as we already defined, it acts as a whole on a single fluid particle, means that the body force is distributed. A body force, let's say if this is our single fluid element, then this body force, and let's say if a body force is acting on this fluid element, then this body force will be distributed as a whole on this fluid element, and in this case the body force will be the weight of this fluid. It will be the weight of this fluid, and that weight is due to gravity. So this is our body force, and if we can write our equation, that is of our F is equal to ma in terms of our body forces, then that equation will look like this, that is the delta Fb is equal to delta m and g. So this force is actually being applied on a small amount of mass that results in the gravitation acceleration. So this is actually the weight of the particle, as you can relate with it. So now writing this equation in the x, y and z axis, that what will this force be, how will we represent this force? So the only directional element in this force is the acceleration due to gravity. So now let's write this body force in terms of the xyz axis, and here the g is the vector representation of acceleration of gravity, and in component form we can write this equation like this. So this is the weight of the particle that is being acted in the x direction, in the y direction and in the z direction, and you can see that the direction is defined by the g here, because this is acceleration, and acceleration can also be represented both with its direction and magnitude because it is a vector. So the body forces in the x direction, in the y direction and in the z direction for a single fluid element that is under the forces of gravity will be like this. So these are our body forces for a single fluid element. Now let's see what our surface forces will be, and surface forces acts on the element as a result of its interaction with the surroundings. So as we already mentioned that, let's say if we have a pipe and in that pipe a fluid is flowing, so that fluid will apply a normal pressure force on this surface of the pipe. So due to this pressure force, some forces will generate, and these forces are called surface forces, as in this case the surface forces are the pressure. So let's say if this is our differential area A, and on this differential area a surface force delta Fs is being applied, delta Fs. So this delta Fs can be resolved into its three components. One will be normal to this area, that is delta Fn, that is normal to the area, and the other is delta F1, delta F2, that is in that plane, that lies in a single plane. So our surface forces that is being applied on a differential area dA can be further resolved into three forces, that is the normal force that is actually perpendicular to this area, and delta F1 and delta F2 actually lies in this plane. So what will happen now, that these forces will in turn generate stresses, and we will represent these forces in terms of stresses. So now let's see that how those stresses will be. As you can see that there is one normal force, so due to this normal force a normal stress will generate. So if this is the direction of the force, the direction of the stress will be like this, and due to this two forces F2 and Fn, what will happen, that here the shear forces will the shear stresses will generate due to these two forces. So in every plane, if we take this as a single plane, in this plane what will happen, that one will be the shear stress that will occur due to this normal force, and two will be shear stresses. There will be shear stresses as well in this direction and in this direction, and these shear stresses will be due to these two forces that are lying in the plane. One is delta F1 and delta F2. So as we saw in terms of body forces, the body forces can be represented as the weight of the fluid element, and that weight can be further classified as the weight along the x-axis, the y-axis and the g-axis. But when it comes to the surface forces that are due to the interaction of the fluid with its surrounding, we can say that that surface force can further be it can be resolved into this normal force that is normal to the plane, and these two forces that lie in the plane, and due to these forces some stresses will generate. Due to normal force, normal stress will generate, and due to the forces that lie in the plane, shear stresses will generate. So that's how we are going to represent these forces, our surface forces. And now let's see a diagram and write an equation that how these normal force and surface force will change from one phase to the other. So now let's do that. So as previously discussed, the surface forces can be resolved into three forces. One will be normal to this differential area, and these two forces will lie in the plane. And due to these three forces, we will have stresses. These forces will result in the stresses, that these are the reaction forces. So the normal stress will be due to the forces that are normal to this differential area dA, and the shear stresses will be due to these two forces F1 and F2 that lie in the plane and that are resultant on this differential area. So what will it be when we represent these stresses on a plane, and that plane is the face of the cube? So how will we represent them there? So this is how they are being represented, these stresses. If we take a plane A, B, C and D, so this plane will have three stresses. One will be normal stress and the two will be shear stresses. So by the two subscripts we are actually representing two things. You can see that the shear stress has two subscripts. So the one is x and the other is x. This x represents the direction normal of this plane. That is the normal direction of this plane in which the stress is occurring. Normal direction of this plane A, B, C, D. This plane A, B, C, D. So this is the normal direction of this plane, and this is what the first subscript is representing. The second subscript is representing the direction of the stress. The direction of stress. And you can also say that for the other notations, that is the shear stress x, y. So this is the direction of the normal to this plane and the direction of the stress. And as you can see, the normal direction to this plane is along the x-axis, and this is the direction of the stress as related to this reference axis. So this is how we are going to represent the stresses on a plane. If we take a single fluid element in the form of a cube and we would like to represent these stresses on the face of the cube, so this is how we are going to represent them with two subscripts. One will represent the direction normal of the plane and the other will represent the direction of the stress. So let's move forward and see the gradient of these stresses. If we take a single cube, if we take a cube and we say that this is a single fluid element, so how will this fluid element behave and how will these stresses behave when we move from the center of this cube to these faces? So how will these stresses change if we move from the center to these faces of the cube? So actually now we will be seeing the gradients of these stresses. These are the normal stresses and the shear stresses in the direction x, y, z, and we will write some terms and then add them up in terms of forces to get our surface forces. So now let's move on and do that. So this is what we are going to do. We are going to represent these for these stresses in terms of our forces. As you can say that stress is equal to force per unit area. So the force will be stress into area. So this is how these terms right here represent, and these this term represent the stress, the shear stress, and these terms represent the area. As you can say, this term represents the stress and this term represents the area. So this was the generalized notation that these are actually represented in the form of forces, the terms you are seeing that are being applied on this cube, and the surface forces. These are the surface forces in the x direction acting on a fluid element. So these are all forces are all in the x direction, and as you can see there are two normal stresses. This is the normal stresses and its gradient. So this is the normal stresses that was at the center of this cube, and as we moved around from this center to this face, this is how the stress will change. This is the gradient of this stress multiplied by the area of this plane, and that is y, z, as it represented right here. So similarly for this normal stress, this is the stress at the center, and as we move in this direction to this face, we will be moving in the negative x-axis, so we will put the negative sign, and this term right here represent the gradient of the stress as we move from the center to the to this face of this plane right here in the negative x direction multiplied by the area. So these are the two normal stresses, and the other, as you can see, are the shear stresses, and its representation as is for this plane right here. For this plane, this is the shear stress and its gradient. This is the shear stress at the center, and as you can see, these two subscripts right here, the z show the direction normal of this plane, that is along the z axis, and the direction of this stress, that is along the x axis, and the gradient of this shear stress as it moves in the x direction, and the area A. Similarly, this stress right here, this represents the gradient of the shear stress along that back plane. So this is the shear stress Zx. Z represents again the normal to this plane, and the x represents the direction of the stress, and this term right here represents the gradient of this stress, and this represents the area. And so for these terms, these are for this plane, this top plane. This is the original stress at the center and its gradient multiplied by the area, and this is for the bottom plane, the original stress and its gradient multiplied by the area. So these are all represented in terms of forces, these stresses, and now we can add them up. We can add all these stresses keeping in mind their direction along the positive and negative x-axis, and if we add them up, we will come up with the forces along the x-axis, and these will be the surface forces that we are interested in. So we will get all the surface forces that are being subjected on this element, this fluid element, in the x direction, and from that we will write equation for the forces that are in the y and z direction. So this is the surface forces along the x axis, and if we add these terms up, if we add all these terms up, this is what we are going to get. So this is the partial change in the normal stress in the x direction with respect to x, partial change in the shear stress with respect to y, partial change in the shear stress with respect to z multiplied by the volume, and these are the forces, the surface forces along the y and z axis. So these are the surface forces along the x, y, z axis. So we can write a single equation for these three forces. If we add them up, means if we take the resultant of these three forces, we can write them like this. So this is the resultant force, and if we add all the surface forces in the x, y, z axes, we will get a single resultant force representing all these three surface forces along the x, y, z axes. And as you remember, this was our equation of motion. So what we are going to do, we are going to add the forces. Here we will add the body forces and the surface forces, and we will equate this to this term in the next slide, and from that we will get our general equation of motion in the differential form for a single fluid particle. So let's do that. So let's write an equation of motion by using these three equations. This was our F is equal to delta ma. So we can write this equation in terms of x, y, and z. That is the equation of motion that represents the forces in the x direction, all the forces in the x direction, and the resulting acceleration in the x direction, and the forces that are along the y direction and causing acceleration along the y acceleration, and the forces that are along the z axis and causing a resulting acceleration along the z axis. So on the left hand side, we are going to add the surface forces and the body forces along the z axis on the x axis in terms of x, and we will going to equate that to mass and acceleration, and we will represent mass in terms of density into volume, because you can remember that density is mass per unit volume. So we will be representing this mass in terms of density and volume. So now let's use these three equations and write our equation of motion for a single fluid particle in differential form. So this is what we are going to get. These are the three equations of motion along their particular x, y, z axes, and this is the body force that is representing, and these terms represent the surface force is equal to, that is the density, and this represents the acceleration, and this is the field representation of acceleration. As you remember the field representation, in which we represent a certain property, the change in a certain property with respect to time and position. So this is the field representation of acceleration, and similarly for this is the body force in the y direction, and the surface forces in the y direction is equal to density and the field representation of acceleration due to the v velocity vector. And similarly, the body forces and the surface forces along the z axis is equal to density and the field representation of acceleration due to the change in v velocity vector with respect to time and position. So this is the equation of motion for a single fluid particle in terms of differential form. So this is we already discussed that we are going to represent the mass in terms of density and volume. This is what it represents, and the volume terms that we saw with these two terms, with these terms right here with the body forces and with the surface forces will cancel out with the volume terms on the right hand side, and this term will cancel out as you saw that in the previous slide. So the volume term cancels out, and the general equation of motion for the fluid is this. These are the general differential equations of motion for a fluid. So now let's put some conditions on this these equations, and let's say we are going to derive these equations for inviscid flow in which the viscosity is 0. So if you take the viscosity 0, the shear terms will be neglected from this equation. So now let's write an equation for an inviscid flow in which all the shearing stresses are 0, and now then see what our general equation differential equation of motion will look like when we apply this condition on these equations. So let's see that. Now again, these are the three differential form of our equation of motion, and now we are going to apply the condition of inviscid flow, and by applying the condition of the inviscid flow on this equation, we are going to eliminate the shearing terms, the shear stress terms in these equations, and this is what we are going to get. This is the body force, the surface force is equal to the density and the acceleration field, and this is along the x, this will be along the y, and this will be along the z axis. And as you can see, the stresses are also being replaced by pressure. We already discussed that stress is equal to negative of E in the preceding lectures, and by substituting the stresses and putting them is equal to minus P, we can write the equation like this, and these equations are called the after putting this condition, that is by putting stresses in the x direction, y direction and z direction and equating them to minus P, we will get these equations as already discussed, and we can further generalize these equations and write them in terms of this, that is the density acceleration due to gravity minus del P. The del will represent all the partial derivative, that is partial over partial x, partial over partial y, partial over partial z is equal to del partial change in velocity with respect to time. This velocity will contain all the u, v, w velocity vectors plus v, here the u, v, w velocity vectors, the del term, that is partial over partial x, partial over partial y, partial over partial z, and the v velocity vectors. So this is the more generalized term, and these are our more generalized equation for our equation of motion for a single fluid particle, and this equation is also called the Euler's equation of motion. So we got the Euler equation of motion by applying a certain condition that our flow is inviscid. By applying that condition, our shearing stresses were neglected, all the shear stresses were neglected from our equation of motion, and then by applying this condition that all our stresses will be equal to negative of pressure. So by putting that condition here, we actually got these equations of motion, and by further generalizing it, we got this equation, and this equation is called the Euler's equation of motion. So this is what we did. We initially considered the linear conservation of momentum, and we say that we will write equations for that, but we represented that equation of motion by using our same Reynolds transport theorem that we derive for the conservation of momentum, and that Reynolds transport theorem, like any other equation, had a left hand side and a right hand side, and we said that we can apply the same right hand side for a differential control volume, a very small control volume, but what we were considered what about the left hand side of that equation, that was the summation of the forces and we further saw that these forces will consist of the body forces and the surface forces. The body forces was the weight of the fluid element, and the surface forces were in terms of our normal and shear stresses. So then we added these two forces, the body forces and the surface forces, and put them in our equation of motion, that was delta F is equal to delta ma, and we got our equation of motion for a single fluid particle. And by putting the condition of inviscid flow, by taking the condition of inviscid flow, we neglected all the shearing terms, all the shearing stress terms from this equation, and represented it like this. And by taking all the stresses as negative p, we put all the normal stresses in terms of negative p, and we wrote a more generalized form of this equation like this. And this equation is also called the Euler equation of motion. So this was what we derived by taking the conservation of linear momentum in the differential form. So hope you understand that, and now let's move forward.